Okay, folks. So I'm going to go ahead and go with homework number 9, which is problems 3, 5, 7, 8, and 9 from the environmental chemistry book. Okay. So let's start by looking at these. Okay, so problem 3. 3 is calculate the titanium concentration in the South Pacific near the island of Fiji. The concentration of titanium in the South Pacific Ocean near the island nation of Fiji is found to be approximately 3 times 10 to the 9th moles per liter. Calculate this into ppm, ppb, or ppt as appropriate. So, it's a simple conversion. We're turning a 3 times 10 to the negative 9th moles in a liter, and we're turning that into some sort of mass over mass. There's really one thing we really need to know, and that is we need to know like the density of seawater being something like it's like something like 1025 grams per milliliter, and we need to know the molar mass of titanium. Titanium being something like 47.867 grams per mole. With that in mind, we can do that. So 3 times 10 to the negative 9th moles in 1 liter. Multiply that by 47.8679 grams of titanium per moles of titanium. That there in 1 liter there is something like 1,000 milliliters, and the density of seawater is something like 1 milliliter weighs 1025 grams. So with that in mind, that's a measurement of grams per grams. Let's figure out what this number is before we go any further. 3 times 10 negative 9 times my 47.8679 divided by my 1,000 divided by my 1025. And this gives me something like 1.4 times 10 to the negative 10th grams per gram. So to get this into a reasonable number, 1,000 is 10 to the 3rd. A million is 10 to the 6th. A billion is 10 to the 9th. So if you go with a trillion, which is 10 to the 12th, that's going to say, oh, I have 140 parts per trillion. Something like 140 parts per trillion. That was number 3. Honestly, that one was very straightforward. Number 5. The principal anion and cations of Lake Huron, one of the Great Lakes in North America, are respectively hydrogen carbonate and calcium. The concentration of the former is approximately 105 millimoles per liter. Calculate the mass of solid hydrogen carbonate that would remain if 250 ml of lake water was evaporated to dryness. So if we have mostly calcium and hydrogen carbonate, and the concentration of this guy is 105 millimoles per liter. Okay, This one is a little bit more challenging. One, if we're going to make a big assumption here that the total amount of cations and anions are just about even, that the total charges are balanced in here. With that in mind, so if calcium is 2 plus and carbonate is 1 minus, that would need something like 1/2 the number of calciums to neutralize the hydrogen carbonate. So that would mean we had to have 0.525 millimoles per liter of calcium. Now, with that in mind, we're going to make another big assumption that all the calcium will precipitate as carbonate. All the calcium will precipitate as carbonate. So we're trying to figure out if this is how much calcium we have. That's also going to be how much calcium carbonate we have. So if we have 0.525 millimoles in a liter, and we're evaporating 0.250 liters, how many millimoles of calcium carbonate would precipitate? So doing that, so 0.525 times 0.25 would have something like 1.3125 times 1. Let's just convert this. Okay. We're going to convert this. If that's millimoles, converting that into moles, that would be something like 1.3125 times 10 to the negative 4th moles of calcium carbonate. Now, how much does calcium carbonate weigh? Calcium, it weighs about 40. Carbon weighs about 12. And then 16 times 3, that's something like 48. So the total molar mass is something like 100 grams per mole. So if we multiply that by 100, if I leave this and turn this back into, that would be a really small number in grams, but if we turn this into milligrams, it's something like 13.1 milligrams of calcium carbonate would be left. 13.1 milligrams of calcium carbonate would be left. So that one's a little bit trickier. That's why the assistance is there to try to guide you so you don't go running completely down the wrong rabbit hole as I originally did. You don't need a KSP, you don't need equilibrium constants, you don't need to figure out the actual concentration of carbonate in present based on pH. Okay, number 7. It's one of those charged ones. If in the particular freshwater sample, the concentration of cations and anions in micromoles per liter is something like sodium, which is +1, 33. Potassium, which is 4. Magnesium, 31. Calcium, 160. Then on the other side, chloride, which is 120. Nitrate, which is 13. Hydrogen carbonate, 270. Carbonate, 0.67, and sulfate, 11. Compare the concentration of the total positive and negative charges in the solution. Assume the difference is due to hydronium or hydroxyl ion and calculate the pH. So if these are in micromoles per liter, you don't have to convert anything into mass. We can just double up whatever is doubly charged. So let's figure out my total cations. So my total cations is 33 plus 4 plus 31 times 2 plus 160 times 2. And that gets 419. My chloride is 120 plus 13. My hydrogen carbonate is 270. My carbonate is 0.67 times 2. And my sulfate is 11 times 2. So that's 426. Well, let's say 34. Okay, that's all in micromoles per liter. Not too different, so the difference, 426.34 minus 419, would be our concentration of hydronium in millimoles. So 426.34 minus 419 was going to be something like 3.4 not millimoles, but micromoles per liter. So turning that into scientific, 7.34 times 10 to the negative 6 molar hydronium. Taking the negative log of that, is 7.34 times 10 to the root negative 6 is going to be a pH, should be pH of 5.134. 5.134. So, that one's actually not too bad, all things considered. Let's look at 8. Okay. The major ions and the concentrations in millimoles per liter of seawater are sodium being 470, potassium being 10, magnesium 2 plus being 53, and now calcium being 10. We have, on the other side, chloride 547, bromide 1, sulfate means on like 28, and then hydrogen carbonate / carbonate unknown. Assuming the charges of these species balance, calculate the total concentration of the negative charges associated with these two carbonate species. With a pH of 8.2, calculate the concentration these individual species have. So pH of 8.2. Now the problem here is we have X of this, which is one charge, and Y of this, which is two charges, 2Y. And these are going to balance. Now, with a pH of 8.2, this is not really going to be of significant values, especially with considering these are millimoles. The millimoles, if you did 10 to the negative 8.2 and divided this by 1,000 to get this into millimoles, or actually multiply by 1,000 to get this into millimoles, it's still a rounding error. If you said 6.3 times 10 root negative 9, and you said, okay, well, what about the base? What about contribution of hydroxide? Well, 10 to the root negative 14 divided by 6.3 times 10 to the negative 9th. Even if I times by 1,000, that's a rounding error compared to all these. Bromine of 1 minus, we're talking about, that's 1 plus 0.00158 rounding error. So let's add this up. Once again, times 2 times 2 times 2. So 470 plus 10 plus 53 times 2 plus 10 times 2. So we have 606 millimoles on the left. 547 plus 1 plus 28 times 2 on the right means 604. So when you minus that, the difference is the sum of both of those things are 2. X plus 2y. Now, because we have a pH and because HC3O minus can be written as a Ka expression of H plus and CO3 2 minus, we can set up that Ka equals X over Y over X times what's the pH of 10 to the negative 8.2. That's 6.31 times 10 to the negative 9th. And Ka for this is 4.7 times 10 to the negative 11th. 4.7 times 10 to the negative 11th. So rearranging that, X over Y equals 6.3 times 10 to the negative 9th over 4.7 times 10 to the negative 11th. 3 times 10, negative 9, 4.7 times 10, negative 11. So the ratio of these two is something like 134 to 1. Okay. 34 to 1. Now, and 34 to 1. So, with that in mind, and we know that, so that we can say that y, 134y equals x. Sorry, I'm running out of space. 134 y equals x. So we can say that 2 equals 134y plus 2y. So 2 divided by 136. 2 divided by 136 is going to give us the concentration of carbonate in millimoles. And I got something like 1.47 times 10 to the negative second millimoles per liter of carbonate. And that means, well, if I multiply that number by 134, I'm going to get something like 1.97 millimoles per liter of hydrogen carbonate. So almost none for the carbonate, a very high concentration, or at least a relatively high concentration for hydrogen carbonate. So that is 8. Number 9, last one. Okay. Number 9. In the open oceans, the concentration of iron is approximately 1 times 10 to the 4th at the surface. Iron 1 times 10 to the -4th ppm at the surface, and 4 times 10 to the -4th ppm in the deep ocean. Now, aluminum is 9.7 times 10 to the -4th ppm at the top, and 5.2 times 10 to the -4th ppm at the bottom. So it's increasing going up and decreasing going down. However, one thing you got to keep in mind is the only input of these things are coming from the surface, where they are not due necessarily to like something coming off the ground layer. So if the main sources of these come from up above, why does iron build up at the below, deep in the surface, but not so much at the top of the surface? And this largely has to do with consumption and oxidation states, and we have the oxygen levels are highest up here, high, oxygen levels low. So low PE, high PE. Okay. For one, iron, most of these guys have hydrous metal oxides that have generally low solubility. And so one of the ideas that at the surface, a lot of this iron goes from iron 2+ to iron 3+, and this iron 3+ then goes to iron oxide solid. So it oxidizes in these particulates and can sink going down. These sink and concentrate down on the ocean floor. Back on the ocean floor where the PE is low, this can reconvert back into iron 2+, and so it concentrates on the ocean floor. So it starts to redissolve. One reason also has to do with maybe iron is a micronutrient that's getting used a little bit higher up, where there's more microorganisms. But aluminum isn't necessarily a nutrient, and so it isn't getting utilized as much, and so it's not really going down. And so we can think of concentration typically decreases with depth, unless there's something that causes it to build up and sink faster as it mixes. Now, aluminum can bind to shells of organisms down on the ocean floor, so it can be uptake in that way, so it can be a little bit lower. But aluminum also doesn't necessarily change oxidation state. So any aluminum that oxidizes to Al2O3 and then sinks doesn't go back. Al2O3 does not change back into Al3+. So any aluminum that crashes out after being oxidized doesn't redissolve back on the ocean floor. It's not really a low enough PE for that to occur. So that's kind of a little thinker, and so there's a couple different reasonable answers for why that is. But that is essentially that chapter. So with that in mind, keep working on that homework.